Welcome to this explainer. Today, we're going to dive headfirst into a truly profound cosmic mystery, and we'll be exploring biological systems through the lens of entropy. We constantly take for granted that our world is just full of living things, right? Stuff walking around, breathing, growing. But when you stop and really look at the fundamental mechanics of our universe, the very existence of life starts to look, well, incredibly strange.
Why does life even exist? It's a massive question, because fundamentally, the existence of highly ordered biological systems, like humans, animals, a giant oak tree, it seems to completely contradict the most basic laws of physics. Literally everything else in the universe is tending toward disorder. It's breaking down, degrading, just spreading out into the void. And yet, here we are, these incredibly complex, highly ordered combinations of trillions of cells and molecules, seemingly defying that cosmic tide. No way, right?
And this brings us to the famous Schrödinger paradox, which pretty much establishes the absolute intellectual stakes of our explainer today. Back in 1944, the eminent quantum physicist Erwin Schrödinger famously said that life feeds on negative entropy. He was essentially asking this pivotal question: how do living things manage to build themselves up when the rest of the universe is constantly, relentlessly falling apart? He theorized that life maintains its complex internal order by basically feeding on this negative entropy, like it's pulling in highly concentrated energy for the sole purpose of avoiding inevitable decay.
Okay, so to solve this mystery, here's our roadmap. We're going to cover 1. The paradox of life, 2. The entropy problem, 3. Life's open system solution, 4. Dissipation-driven adaptation, 5. Engines of order, and finally, number 6, asking, is life inevitable? Let's jump right in.
Section 1. The paradox of life. Physics versus biology.
To truly grasp Schrödinger's question here, we really have to realize that physicists and biologists use completely different languages to look at the exact same clumps of atoms. When you look at an object out there in the world, physics doesn't just automatically draw a bright line between what is alive and what isn't. For example, if you drop a cat from a tower, and seriously, please do not try this at home, asking if that cat survives is a biological question, but asking how fast it falls, what its mass is, or its kinetic energy upon impact, well, that's a purely physical question. Translating between these two conceptual frames, taking biological concepts like survival and reproduction and expressing them in the hard physical measurements of energy and time is where the real mystery lies.
Moving right along to Section 2, the entropy problem, the second law of thermodynamics.
Now, this translation between biology and physics gets incredibly tricky when we run into the ultimate physical rule that governs our entire universe. Entropy increases simply as a matter of probability. Energy naturally just tends to disperse and spread out as time goes on. Think about it like a physical space, right? There are vastly more ways for a room to be totally messy than perfectly immaculately neat. It's exactly why hot coffee cools down, why gas diffuses through the air, and why an egg will easily scramble, but it will never ever spontaneously unscramble. The universe overwhelmingly favors disorder simply because there are infinitely more ways to be disordered than ordered.
Which brings us to Section 3, life's open system solution, breaking the rules.
So, if the second law guarantees that absolutely everything degrades into this messy thermodynamic equilibrium where energy is entirely uniform, what is the secret to life? How do we exist and breathe and grow without breaking the fundamental laws of physics? Well, the second law spells absolute doom for a closed system, like a hot cup of coffee trapped in a sealed room, which is inevitably going to cool down until it matches the air around it. But life is an open system. Living things constantly exchange energy and matter with their environment. We aren't sealed off at all. We are continuously importing highly concentrated energy to maintain our internal order and basically keep the chaos at bay.
So a plant doesn't violate physics at all, not even a little bit. It absorbs extremely energetic, highly concentrated sunlight, uses it to build complex structures like sugars, and then spits out degraded, disorganized infrared heat back into the universe. Overall, the total entropy of the entire universe still goes up. But the plant buys its own local, highly structured order by making its surrounding environment far messier. It's this incredible cosmic trade-off: local order paid for by universal chaos.
Let's move to Section 4, dissipation-driven adaptation, Jeremy England's theory.
MIT biophysicist Jeremy England proposes that life didn't just accidentally stumble upon this brilliant process of energy exchange. His theory of dissipation-driven adaptation suggests that when a random clump of atoms is bathed in a heat bath, say a primordial ocean or a thick atmosphere, and then it's blasted by a massive external energy source like the sun, it will inexorably restructure itself to dissipate that energy. Basically, it will naturally adapt to become better at absorbing and dumping heat. It's almost like a river naturally carving a canyon over thousands of years. Matter just finds the absolute most efficient path to let the energy flow right through it.
And the cool thing is, we actually see this physical phenomenon of matter self-organizing all around us, right under our noses. Snowflakes, sand dunes, turbulent vortices and fluids, they all share this incredible characteristic. They're strikingly patterned structures that emerge completely naturally when a group of particles is strongly driven by a dissipative process, like the wind or viscous drag or rapid condensation. The universe just naturally builds patterns to move energy around.
Which takes us to Section 5, Engines of Order, how life repairs itself.
While sand dunes and snowflakes are fascinating, biological living systems take this physical phenomenon to a spectacular extreme. They act as highly optimized engines of order that have to constantly fight off a continuous, destructive bombardment of thermal fluctuations. This builds a continuous, cyclical engine that defines how life survives. First, you absorb highly concentrated energy, whether that's sunlight for a plant or, food for an animal. Second, you use that exact energy to perform internal work, organizing your cells and executing vital self-repair. And third, you expel the degraded, messy heat back out. Living structures are constantly bombarded by thermal fluctuations that act like a bull in a china shop, actively trying to tear those cellular structures apart. So this cyclical work perpetually drags the organism's physical structure back up the mountain every single time it slips toward decay. Without continually burning fuel for these repairs, a cell would irreversibly degrade into just a dead, amorphous soup of molecules.
So instead of trying to broadly define what life is right from the start, physics looks at specific behaviors. Things like making copies of yourself, extracting energy from difficult sources, predicting the environment based on past statistics, and maintaining homeostasis. By analyzing these really specific traits, physics proves mathematically that two energy-dissipating self-replicators are far more thermodynamically efficient at releasing energy than just one. Life isn't just surviving, guys. It is absolutely maximizing the flow of energy.
And this leads us to our final segment, Section 6, Is Life Inevitable? Reframing Evolution. Because this physics-based perspective gives us a truly mind-bending conclusion about the origin of life itself, we kind of have to completely reframe how we view evolution. From a strictly thermodynamic perspective, it's not just Darwinian survival of the fittest anymore. Natural selection also favors the most energetically productive. Think about it. A highly structured, intricately organized tree with sprawling leaves and deep roots is just vastly better at capturing and routing solar energy into degraded infrared heat than a random scattered heap of carbon, nitrogen, and oxygen atoms.
Jeremy England actually suggests that life isn't some magical exception to the laws of physics, nor does it require a colossal stroke of luck. It is a spectacular, inevitable expression of matter naturally rolling downhill. When the conditions are right, the physical laws of the universe practically demand that matter will organize itself to dissipate energy. Life is, essentially, just physics doing what physics does best.
So, I'll leave you with this provocative thought to ponder. If life is essentially just a highly complex engine born from the rigid laws of thermodynamics, constantly working to increase the ultimate entropy of the universe, how does this change your definition of being alive? The boundary between physics, biology, and what it fundamentally means to exist is blurring right before our eyes. Thank you so much for joining me for this explainer. Keep wondering and keep looking closely at the incredibly strange world around you.